Okay, so continuing on with the conference, welcome if you're just joining us. I'd like to extend a warm welcome to Peter Riley and Damien Lopez from Decision Lab, who will present on using reinforcement learning to solve a variation of the 3D bin packing problem. Welcome, guys.
Hi, and thank
Take
you.
it away.
We've already had our introduction, but I'll be presenting myself, Peter Riley. I'm a senior consultant at Decision Lab, and I did the simulation development on this project alongside Joy Kuo, who also did the simulation development. She won't be presenting today, but will be on hand to answer questions, and we'll post all our contact details at the end. And then finally, we have Damien Lopez, who's a senior consultant at Decision Lab, who did the reinforcement learning aspect to this project. So yeah, we're about to explain how we used reinforcement learning to solve a variation of the 3D bin packing problem. So we'll start off with an introduction to Decision Lab and who we are as a company. Then we'll explain the problem statement and what the traditional 3D bin packing problem example is and what is our variation of it. Then we'll explain a bit more about what the sim did when we built it in AnyLogic. And finally, we'll explain how we integrated that with Microsoft Bonsai to train a reinforcement learning agent. So who are we? Well, Decision Lab is an award-winning technology company, and we just celebrated our 10th birthday this month. We solve challenges using innovative and useful solutions, using simulation reinforcement learning, which is obviously particularly relevant for this project, but we also do things with mathematical modeling, optimization, data science. Our efforts and models have been rewarded and recognized with the Financial Times Management Consultants Award for the past 2 years. And we're also an integration partner with Microsoft Autonomous Systems since July. So the problem. So the standard 3D bin packing problem is that you have cuboids of varying sizes, and your aim is to place them into a bin, which can be like a container or a pallet. And the idea is that you want to maximize the utility of the bin, which is effectively saying you want to minimize empty space. So this is, clearly relevant in real life in various different scenarios. In fact, we'll mention a bit later on how we've actually tried to tackle a variation of this on real life in a slightly different project. In that project, we already have this kind of human baseline that they're only able to pack boxes to 50% utility using their own kind of human intuition. So clearly there's an opportunity for simulation, reinforcement learning, or optimization to come in and improve that efficiency, which in turn is going to do things like reduce packaging waste and reduce the travel time that you're going to have to need, because we would be packing less boxes onto a truck, which is overall going to reduce things like fuel consumption. What is our variation, though? So there's a standard example, but what the problem that we're trying to tackle specifically is where item arrives in a sequence. So you can think of them arriving on a conveyor belt and they're not all present at the beginning. What the reinforcement learning agent sees is you kind of imagine the conveyor belt coming around a corner, as you can kind of see on that diagram, where you can only see the current item and the next item. And you have to deal with them in turn. You can't ignore or put to one side. And finally, I think we've got this constraint that you have to place items in a way that wouldn't topple over. So things have to be stable and sensible, not floating in midair or precariously placed above another box. So kind of mentioned there that we have two ways that you might tackle a 3D bin packing problem. Traditional optimization can be used for the more standard example, but in particular, Decision Lab ourselves have worked on more of a standard example of this to create a logistics optimization, logos we call it, for effective item packing in deployed military logistics hubs. But within this specific variation, the key difference is that there isn't an overall view of all of the items at the beginning of the model run. So there isn't a way that traditional optimization should be able to consider everything available and pack it as best they can. So the simulation itself involves three key agent components, which we've created in AnyLogic. So we have items, which items can be of varying sizes, or we can specify fixed sizes, and we pack these items into the bins, and then the bins are located within packing bays. So a packing bay is like an area that the packer has access to, and as soon as a bin is complete, so we typically in this example we say a bin is complete when it has 80% utility. At that point, the bin gets sent and removed from the packing bay, and it gets replaced by a fresh empty bin. And then also the actions to take. So when we're making a decision, we have to choose which of the available bins we want to pack into. And then when we've decided upon the bin, we need to decide the X and Y coordinates of where exactly we're placing the item in the bin. And we're kind of assuming that this is sort of like a Tetris idea of the items sort of get dropped down and will rest on whatever's underneath them. So that's the reason that we're not specifying the Z coordinate as well. So this is one of the views that we have of the model running, where you can see the items arriving on a conveyor belt, and they get packed, and some of them get rotated and placed into the bin. You can see we have on the right-hand side of the screen, we have a display showing the current actions that are being taken. And we also have some KPIs to judge the performance. So we're particularly interested in how many items can we pack into the bin, what is the total volume of things we've packed, and what is the mean bin utility. So how does this link into Microsoft Bonsai, and why did we choose to use Microsoft Bonsai? Well, Microsoft Bonsai is a reinforcement learning toolchain where we can build, train, and deploy brains that can take these actions that we want them to. So it's a particularly useful platform that is easy to use for subject matter experts. So and the people who want a kind of easy interface to be able to code in their states and their actions and their rewards, and then it allows a way to visualize things in graphs, and we can basically assess all the training all through that platform itself. And in particular, and particularly relevant to this conference, it integrates very well with AnyLogic, and it's simply just a case of clicking export within AnyLogic, and then that creates a zip file, and then we just upload the zip file of the exported model to the web interface to our Bonsai workspace. Bonsai has a lot of automatic default settings that are very good to just get something going and working. So it's quite out of the box in that sense. But we can go to a much more detailed level of customization if we need to. So in particular, we were looking at things like how we can tweak the rewards and the goals, and also the DRL algorithm that we actually use. We sort of tweaked all these things during the process to see if we could improve the training. And finally, we use Microsoft Azure to export the simulator, which can be which we can then use the cloud computing power to run the simulator in parallel, and that allows for much faster training. So the model itself has various different run modes in AnyLogic. So we have a user placement mode where there's an input database, and row by row we're specifying the exact dimensions of an item and what's the order of their arrival and where should they be placed. So this is the kind of baseline mode that it's a mode that we use to sort of verify that everything is going as expected, because this is a very deterministic mode. Then we have a rules-based mode, which is able to deal with random item dimensions. And this rule-based algorithm was taken from an academic paper that specifically it was researching into 3D bin packing algorithms. So it's quite sophisticated and acted as a very good baseline for what we were then comparing to the Bonsai modes. So we have a training mode where we can, it's got quite a lightweight AnyLogic mode where we turn off the visualization and we're just able to simply train and get everything we need in terms of the states, and then we can apply the actions or from the Bonsai side of things. And then when we train the brain, we export it and host it as an app service. And specifically, so we've specifically used the app to then play back all of our actions. So that allows us to view what's going on, which we'll see a bit later on as well. We've got a video of the trained actions. But I think as well, it's important to mention that it's easy to see how that could fit into like a wider a business context of we would be able to query this web app, and then we would be able to return the best action. So that could kind of fit into like a business supply chain where we could be like directly feeding employees, packers, who would then know exactly what action to take and where to place their items. And this diagram just sort of reinforces all of that and brings it together. That you can see on the left we have the simulator, and that is connected to Bonsai and how we train it using Inkling, which is the special Microsoft code that's suited to Bonsai. And then we train it, and then when it's trained we export the brain, and then the exported brain can then we can then apply and view all of the trained actions in the simulator. So that's the simulator, and now I'll pass you over to Damien to talk a bit more about the reinforcement learning.
Thanks, Peter. So first we're going to talk about when and why we're going to use reinforcement learning. So reinforcement learning is a control optimization technique very useful when the performance of a sequence of actions can only be measured after a long period of time. So in our scenario, we can only really see the effectiveness of our technique once it's been fully packed, and we can evaluate how much utility was achieved, so how much left space there really was, and we want to minimize that. It's also particularly useful when your present state, when the decision made in the present state affects the next state. So in this problem, placing an item down in the bin greatly affects the decision that you'll make in the next state, because the entire your possibilities of where to place the item are going to change quite significantly. Also, optimization is really only useful when you have all the information at time zero, but reinforcement learning really is applicable when context matters. So your current state affects where you need to be in the next state. So we can't really just do it all from without any knowledge of where we are currently. We also are able to deal with partial observations. So like we've said, we only are allowed to see the current item and the next item rather than seeing everything. So reinforcement learning works better when you have this partial observations rather than having known everything at one time. It's also pretty proficient with dealing with stochasticity, where we have random items coming rather than a set sequence. And when we have multiple goals, such as maximizing the amount of bin utility, or when we want to have adaptability to an environment, so say we change the type of items that are coming, the dimensions that are available, it's pretty useful. And it's especially powerful when a simulator is available, as reinforcement learning really requires a lot of training and a lot of experience. So when a simulator is available that we can scale up, it becomes very powerful because we can really retrain very, very quickly for new environments. So, next one. So here's the typical reinforcement learning flowchart. We start off with our agents, which then performs an action in the environment, and then the environment produces the next state and progresses. And we also give the agents a reward or a penalty depending on if it was a good action or if it was a bad action. Then taking this reward and the state, it learns whether it did good or bad, and then modifies that for the next state and chooses the next action, and so on and so forth, until we really get a very good trained agent. It's similar to how a baby learns, in that you teach it to do things and give it like a treat or some form of punishment, whatever that may be, and it learns how to behave. It's the typical way of doing things. So we have a couple of configurable parameters available to us, namely the bin dimensions, which we have scoped between a 1x1x1 box to a 5x5x5 box. And then we can also vary the item dimensions, which can be anywhere between a 1x1x1 all the way up to a 5x5x5 if you really want to, although it's not really tenable in this type of scenario. We can also vary the number of items available to be placed on the conveyor belt, and also the number of bins available to be packed in. The observations are a combination of the height map of each bin, which is how high the quantity of objects are on each XY coordinates. So if we see in the height map there's 5, 2, 5, 5, 2. So that means in coordinate 0, 0, there are 5 it's 5 items high, whereas in coordinate 0, 1, it's 2 items high. And obviously when it's 5 items high in a 5x5x5 box, it's at its max capability. We also then get these feasibility and rotated feasibility maps. Now these were put in place because currently in Microsoft Bonsai, action masking is not possible. However, it is in the pipeline. These feasibility maps allow us to state which coordinate we can place the item in, which will not result in a topple or a fail condition. So for instance, with the height map now, with the feasibility map, that is where you get the item as it comes off the conveyor belt and you do not rotate it. Obviously, with a 1x2x1 box, you cannot put it in coordinate 0 because there's already a 5x5x5 there. However, because it's 2, 1, you could maybe put it at coordinate 0, 5 on the far right in that current orientation. With the rotated feasibility map, obviously, if you rotate the item by 90 degrees, the entire place of where you can put the item completely changes. And this really changes our reward quite significantly. So we'll go through that now. But we'll go through the actions just to understand what we can do. So as we said, we can rotate the object through 90 degrees in the XY plane. We can place the item at a specific X and Y coordinates. And we can also choose which bin to place the item in if there are more than one bin. However, we decided for the purpose of this training to limit ourselves to one bin. The reward is quite simple because as we use the feasibility maps, we are able to more easily state whether it did well or not. So the agent is rewarded by the change in bin utility, which is just how much the volume of the item is with respect to the total bin size. So in this case, with a 5x5x5 bin and a 1x1x1 item, it's a 0.008 change in volume, and then we multiply this by a factor of 10 to get the percentage of how much it changed, and then we give this as a reward for placing that item down successfully. If the item was not placed in a successful or feasible location, then the agent gets a penalty of -1, and the episode is terminated because either the item was placed outside the bounds of the box or overlapping the bounds of the box, or it toppled, or it just exceeded the height limits. So next one. So we had couple of ways to train this. We could have used Apex DQN, SAC, or PPO, and we chose Apex DQN because it's an off-policy algorithm and therefore more sample efficient. SAC had similar performance, but we just decided to use Apex DQN in the end. PPO was considered, but due to it being an on-policy learner, it was sample inefficient, and learning took much, much longer. We used reward-based learning rather than instantiating goals in Bonsai. The reward function was merely to place the items in locations that were deemed valid by the feasibility map. And as a reinforcement learning agent aims to maximize the total number of rewards over an episode, it was directly incentivized to maximize the amount of items it could place in the box. So just by doing this type of reward, we conditioned it to get the behavior that we wanted, just by placing it at valid places. The agent was also trained in a series of lessons. So we started with a 1x1x1 box and a 5x5x5 bin. And once it got to sufficient capability of doing that, up to a utility of 80%, it moved on to placing variable item sizes with different dimensions in length, breadth, and height. And we put those into a 5x5x box as well, hopeful to get it up to a 80% utility, which it did. So going on to the results. We can see that in the beginning with the lesson of 1x1x1 items in a 5x5x5 bin with our reward-based reward structure, we got very good performance after nearly 300,000 iterations, which this took about 1.5 hours to train, which is very fast. It was quite a significant gain over the goal-based iteration that we attempted. Then when it moved over onto the variable dimension sizes of length, width, and height, the agent took only about 7 million iterations to finally get to its final capability. Now you'll see it goes up to 16 million, but that's because we allowed it to try and improve as much as it could over a 10 million iteration sample size. However, because it got there already in 7 million, it just carried on. So this took about 2 days from zero iterations to 16 million, but the 7 million was about just merely a couple of hours. The training was really good because, as you can see, the reward is 10, and now that 10 means 100%. So the agent was actually able to train to such a point where it would fill up one box up to 80%, send that box off for delivery, if you will, and then continue filling up another box well over the total mean bin utility. So to get over 80% with the restrictions we've placed on it is extremely good. But we can get into that now. Going through the benchmarking and performance, we've benchmarked it against the rules-based algorithm Peter mentioned earlier. So with 1x1x1 boxes, it's actually very simple, as you can imagine, just to place the boxes in a unit quantity around. With both rules-based and the Bonsai brain that we trained, both were able to pack all of the items that were available to it and get up to the 80% utility that we desired. Now, an interesting thing that we will go through next is that they did it so in slightly different ways. When we changed the item size to vary its length, width, and breadth between dimensions of 1 and 2, the rules-based one severely underperformed compared to our Bonsai brain, with only 25 items being packed in total, with a total packed volume of 83. You can imagine with the different item sizes. The Bonsai brain, however, was able to pack 80 items and a total packed volume of 272, which is a fantastic result when you take into account it can only see one box ahead with such complicated dimensions. The experiment was also conducted with a random sampling of item sizes, so it's even more impressive than we had anticipated. Now we're going to show some videos of the agents performing. On the left is the rule-based, and on the right is our RL agent with 1x2 boxes. So as we can see, the agent on the left is packing very uniformly, with putting things in the top left corner as it would, and is a lot more organized, whereas the RL agent on the right is really putting them in a more haphazard, disorganized way initially, but I mean placing them in not a systematic way, but we are getting better performance. As we can see on on the left, the rules-based agent was only able to place 75% utility before stopping, whereas the RL agent was able to, first of all, get up to 80% on that box, send it off, and then start packing a new one, which is significantly better than even the rules-based one was able to have. And despite having less space for more items available in the rules-based box, the actual benefit is that it could actually pack more with the reinforcement learning agent. The thing is, this reinforcement learning agent really works better in the real world, because despite having an optimization-based approach versus anything else, this is more and more realistic, because we would normally only have access to this information. In our current climate, we have supply chain issues with truck shortages and people shortages. So to help make efficiency gains, the ability to pack these items into these boxes at a much higher rate than the human baseline of 50% is well established, because we get gains we get environmental benefits, cost benefits, and we don't have to send as many transport. It is really beneficial. So thank you for your time. The 10 and 1 and -1 numbers.
Hi there. Thank you, guys. Yes, just a couple of questions coming in. I'm sure there will be a few more. We've got 2 or 3 minutes here before.
Okay. So the 10 is actually 10 times the bin utility. That it was designed because if we multiplied it by any more, it'd just mess up the scale. So because the utility is just zero, well, the volume of the box divided by the volume of the bin, the times 10 just means that we get the percentage of what it is. So if you have a final reward of 8, that means 80%, and that works much better. And -1 is a significantly higher reward than just a single box. -1 is a significantly higher penalty than a single box would ever have. So it's a severe penalty, and it knows not to do that again.
Okay, great. And question just in from Steve Orr. He's asking, how are these reinforcement learning results used in practice?
In practice. Peter, do you want to handle that?
Yeah, so what I was trying to allude to a bit before is that when we train the brain, we export it as a web app, and it can be deployed as a web app service. So the result of all the training is that you have a web app that you can query with the specific scenario that you're facing right now, and it returns the optimal action that you should take. So one way of doing this is by using the playback mode in AnyLogic, but there's nothing to stop anybody from using the deployed web app in a different way, integrating it in a different way, so that they can, for example, query the web app and get the results to display on a phone or something. That, for example, a packer in a warehouse could be viewing an app on their phone, and they could see the optimal positioning.
Super. Thank you very much, guys. It's very interesting, and I'm sure that people will have more questions and be reaching out to you on the platform. So please stick around, and we'll catch up with you later. Thank you very much.
Thank you.
Okay, for people staying on this stream, it's coming to a close on this stream, but the conference is continuing. In fact, it's transferring now to another stream, and you will find in the agenda that it's going to be AnyLogic 8 and the new features, as well as Python and AnyLogic research and development. So not to miss it. We have the head developers there, and CEO Andre will be all presenting. So please go to the agenda, click on the AnyLogic 8 event, and join the new stream. Thank you for being with us.